Good afternoon, everybody. It's 1 o'clock Central Time. Today we're doing a webinar through the private well class called Groundwater and Well Construction 101. I'm Steve Wilson and Katie Buckley's with me. We're at the State Water Survey at the University of Illinois. If you're not familiar with the State Water Survey, most folks even in the state don't seem to be. We're similar to our State Geological Survey, which every other state has. Illinois just also has a water survey that houses the state's well logs, has a public service lab for sampling wells, and we do a lot of groundwater and well work. So the private well class is funded through the US EPA to a grant to the Rural Community Assistance Partnership, and I'll mention them more in a minute. I do want to mention first off that our webinars have tended to run long. The last several have been close to 2 hours. So we've addressed that and talked to NEHA for those of you looking for CEUs, and we have them approved now, I believe, for 2 hours of credit. So yeah, let's get started. Okay, so today's webinar is part of a national program. I mentioned Rcap, the Rural Community Assistance Partnership. We have a grant through the US EPA to support private well owners. Rcap is a organization that does technical assistance and training all over the country. They have staff in every state. We're kind of the online portion of the program, and Rcap, along with some other partners, are the boots on the ground, if you will, related to helping private well owners. The materials today follow our private well class, but they're not the actual class. Our class is a 10-lesson, once-a-week emailed course that you can sign up for. If you haven't taken our class, I recommend you do so. You'll get a lot more out of that than you will these hour-and-a-half webinars. And we do record each of these webinars. There's 80 some now on our webpage, and those are available on privatewellclass.org or on our YouTube channel. We will have time at the end for follow-up questions. So if something that I say today doesn't resonate or raises a question, we have a chat box and a question box that's on the GoToWebinar window that you have. Put your question in there, and Katie is going to monitor that and create a list of those questions, and we'll pull them up at the end. Yeah. So for those of you that are getting on the webinar for CEs, continuing education through NEHA, I just want to remind everyone that you can't take the same course with the same core content only once during each credentialing cycle, which runs 2 years. So if your credentialing cycle just started on 12/1/21 and you take the course today, you can't get credit for the same course, Groundwater and Wells 101, until after December 1, 2023. We're also an Illinois LEHP credit provider, and if you are interested in that, you're an Illinois EHP, please email us at info@privatewellclass.org. and we can work with you. And the past 2 times we've offered this webinar were on, are listed there in the bottom right. And so you should know your credentialing cycle through NEHA. So again, I'm Steve Wilson. I'm a groundwater hydrologist at the Water Survey, and Katie Buckley is also with me. She's our Water Resources Outreach Specialist. She's going to be fielding questions. She will work with you with your CEs. And I also want to mention Walt Kelly, who's the head of the groundwater section here, who helped answer some of the questions. He's also a geochemist and has a lot of experience with testing and knows a lot more on the chemistry side than I ever will. So we appreciate his help. I mentioned Rcap. It's a Rural Community Assistance Partnership. Each of these colors here represent a region. There are 6 regional affiliates. They're all nonprofits of their own that make up the network with a national office in DC. And so whichever state you're in, like I'm in Illinois, so we work with the Great Lakes Community Action Partnership. They have staff in all 8 of their states, maybe there's just 7, including, I believe, 5 staff in Illinois, and they help with boots on the ground type of efforts related to private wells. We do well assessments, so if you have a problem with your well and you're concerned or you just like to know more information, they'll work with you one-on-one and come out and do an assessment. And that's totally up to you. It's voluntary. And they also work with organizations and groups and counties to put on workshops. So if you're thinking about putting on a private well workshop for the folks in your local area, you can contact Rcap and they will gladly work on developing a program with you if that's what you want, or providing speakers or doing some logistics. or just to come talk about their program, so that you can support your private well owners if you're a professional who works with them. And you can always contact us at info@privatewellclass.org, and we can get you in touch with the right person in your state or in your region. I bring this up. This is the first page of the well assessment. It's an 8-page document. You fill it out. You can fill it out either electronically or by hand. It's not for the well owner to fill out. It's for the assessor, whoever that might be, and Rcap folks are trained to fill this out. It's actually very detailed, and it requires a lot of wherewithal related to private wells to even be able to fill it out correctly. And so it's on our webpage under assessment. And if you are interested in having that done again, we can refer you to the right folks if you email us and would like to have one of those assessments completed. And again, that's all funding through US EPA, so it's all free to you, and all the information is confidential. So the assessment is like a sanitary survey, if you're familiar with those, for a community water supply for private wells. It doesn't have any, it's all voluntary. It doesn't go to anyone else, but it's a chance to also educate well owners about their specific situation. And what I can tell you about private wells is rarely do you find two that are the same, no matter how close they are, or it's just there's always different situations, whether it's treatment or the type of pipes or the well itself, or what they store nearby, or there's just a lot of things with wells that are very different every time you go to one. But it gives you a chance as the professional to promote best practices. There's questions on there that lead really into testing every year, and what backflow prevention devices are and things like that. So it's really a good way to encourage communication and help well owners understand and develop an awareness of issues, as well as understand that there are local sources of help for them, and that they shouldn't be concerned about calling their health department or other agency to find out more information. Everybody's here to help you as a well owner. They've done 2,800 of these assessments around the country. We've also done a bunch of workshops to educate other professionals on how to use it. We do this webinar, it's a 4-hour webinar. We do it once or twice a year. That includes training on this assessment. We actually are doing one on the 15th. We do have limited sign up because it's interactive. And so, but if you're interested in that, you can contact us. And again, the whole idea is to develop partnerships really everywhere. It's the only way to get things done. There's, 23 million well owners out there, and that's a lot more than any one group or one agency or one whatever can deal with. And so we all really need to work together and partner in order to reach everyone. So the State Water Survey quickly was started in 1895, so we're 126 years old. We were established because of cholera and typhoid outbreaks that were occurring around the state. And so we began at the chemistry department at the U of I testing water for those things and trying to improve conditions. This is really before common community water treatment or wastewater treatment. And a lot of our early work through the 20s and the 1920s was related to helping communities get water supplies, improve their wastewater systems, and understanding where the causes and sources of typhoid especially were. This is an example from 1913. These are typhoid outbreaks by year in Quincy, Illinois. And you can see there in 1891, they installed a filter plant, and it really reduced the number of deaths from typhoid. There's other examples of this from our records. I like to show this slide. The black square thing up there is a glass plate slide. This is the way slides were done. This is from, again, around 1913. And there was a big outbreak of typhoid in Rockford, Illinois, and we went so far as to investigate all the possible sources, including milk, which was common because everyone got milk usually from one large container from their local source. And so this investigation was of E. Erickson's dairy route to look at which cases occurred, if he may have been a source or their milk may have been a source of some of the typhoid outbreaks that they had there. Pretty cool stuff. We did a lot of sampling. A lot of people, you can see the tin cup if you look closely on the bottom at the end of the wood there. Everybody just came up and drank out of the old hand pump, and we were there taking samples, and you can tell this was quite a long time ago. Same with well drilling. We helped decide where people should drill, all those sorts of things, and the drilling industry's come a long way from this system here, which is pulleys and an old steam engine that you can't see in the background that's powering this whole thing. So as a private well owner, getting to our topic today, the real things you need to remember as private wells aren't regulated. It's really up to the owner and user to be sure the water is safe to drink. And what I mean by not regulated, that means after it's installed. Many states have regulations on how wells are installed, testing before they can be used. But once they're put in service, there are very few regulations, and it's really up to you. And any wells that may have been put in prior to the current regulations were grandfathered in. So for instance, I grew up on an old hand dug well. My grandpa hand dug in 1933. It was only 14 feet deep, and it was brick lined. When it rained hard, we had cloudy water. It was totally unsafe. But that well will never be improved, or would have never been improved, because it's not required to. And my dad always swore it was better than city water. So that's another story. It can be the best tasting and safest water in the world, but contaminants many times can be colorless, odorless, and have no taste. A good example of that is arsenic, which is a very common constituent in groundwater. It's the 7th most common element in the Earth's crust. And not every state has it, but we see it in pretty widely across the country, at least at low levels. So now I live in town on a community water supply, and the $40 or $50 I pay every month is the cost spread out over the 150,000 residents we have for sampling, maintenance, infrastructure. So when I turn on my tap, my water has pressure and it's clean and safe to drink. As a well owner, that's your responsibility. You need to be a steward of your aquifer and your well, provide maintenance, and test regularly to make sure your water is safe to drink for your family. And really what the point of our whole program is, it's about being aware. It's understanding, you need to have your log, your well log, if it's available, understand what's in it, so you know where your water is coming from, how deep is it coming from, what's the pump setting, does it have a screen, how much pipe does it have. You could have a 300-foot bedrock well that's only got 20 or 30 feet of pipe. That's not nearly as safe as a bedrock well that's 300 feet deep and has 200 feet of pipe. We'll get into that a little bit. So there's also naturally occurring contaminants that has nothing to do with your well not being properly constructed or a local source like a septic or a feedlot. It could just be, again, natural occurring arsenic or uranium or radon. There's a lot of things in the ground that end up being concerns for well water, as well as city water that have to be treated and tested for. And the other two things that we hope come out of our class is it will help you understand the basics so that you can ask the right questions and you know enough about your well that you can figure out whenever you have issues, who to contact and what your local sources of information are. And then lastly, again, you need to sample your well regularly to really understand and know what you have, because things can change, and that's just the way it is. So we're going to talk a little bit about groundwater. And so if I have this box of sand, which is on the left here, water flows through the grains of sand. And this is, in areas where I live, we have glaciated geology. So the upper 200 feet or so is above bedrock. It's all unconsolidated, sand, gravel, silt, clay, and fine material. So water flows through the sand. So an old river valley that fills up during a melting of a glacier may have 150 feet of sand in it, and that stores a lot of water. If I had a jar of sand in my hand, a mason jar full of sand with no water in it, the pore space there is about 30% if it's uniform sand. So that means if I have 100 feet of sand in an aquifer and it's full of water and I take all the sand away, I still have 30 feet of water. So it's a tremendous amount of volume. And you see along river bottoms where it's all sand, or in areas where there's a large sand and gravel aquifer, a lot of times irrigation wells, that can pump 1,500 to 2,000 gallons a minute, and that the aquifer can sustain that because there's so much water available. And so how you determine how good an aquifer is one on porosity. How much pore space is there based on the volume of material. And so in a bedrock system, water doesn't flow through bedrock. It flows through the cracks and fissures in the rock. It's really like pipe flow. So depending on how many cracks and fissures and connections between them there are, when you drill a bedrock well, you may only hit one fracture, and it may only produce a few gallons a minute, or you may hit multiple fractures. We have aquifers here that are in bedrock that'll pump just as much, 2,000 gallons a minute. because they're so connected and the fissures are large enough and interconnected enough that they can pull that much water to a well. So it really matters on the type of rock or the type of porous material you have. So if it's well-sorted sand, it's got more porosity than poorly sorted sand, although this diagram doesn't make that clear, because sometimes the smaller grains fill up the places between the larger grains. And in bedrock, it matters whether you're in limestone, granite, dolomite. It depends on what it is. Granite, for instance, is which if you're in a mountainous area, a lot of times you may be using a granite aquifer. They're known for having very few fractures and very small fractures. And we see, like in Colorado in the mountains, folks who contact us that are only able to get a half or a gallon a minute from their well. Versus if you're in Tennessee or Kentucky or Southern Illinois or Indiana, where it's a lot of karst, a lot of caverns, Mammoth Cave, all those sorts of areas. Water, the bedrock is soft enough that as water moves through it, it dissolves some of the rock and gets rid of it. And that's why you have the large caves that we have in those areas, actually all over the country. And so those store water. And that's good in one way. The other way, it's bad because those fractures go all the way up to the surface. And a lot of times there's no overburden to protect it, no soil. And so you have direct infiltration of surface water down into those deeper caverns, and that's used for water supply. So we see in karst areas as many as 80% of the wells, well, in one of our counties it is 80% of the wells have coliform problems, and that's because it's a livestock area and it's all karst, and there's direct pathway down into the aquifer from the surface. And so you need to know what type of geology you have and understand, along with your well construction, how that affects things. So the other property of aquifers that's important to understand is permeability, and it's kind of the ease that water can flow through the different material. And so one is porosity, how much pore space is there to even hold water, and the second is how fast can it move through that particular aquifer. And so this is an example from Texas AgriLife Extension for their well owner handbook. Gravel is much larger grain, so it has larger pores. Water can move through that up to 3,000 feet in a day, depending on the head difference, which is the water level difference from the high end to the low. And again, sand, depending on how fine it is and how uniform it is, it's still, feet per day in most cases. Then when you start getting into smaller materials like silt and clay, they're less permeable, and it can be, as it shows here at the bottom left, as much as little as 1 foot in 10,000 years if it's a really tight clay. On the bedrock side, all the permeability is in the fractures, so it really depends, again, on how fractured it is. But sandstone is a unique type of bedrock that's soft enough and it has enough sand in it that you can have some secondary water storage. And so it's usually a little higher, provides a little more water, and it moves a little faster. So it has fractures as well as a little water storage. But when you get into like shale, is basically cemented clay. It's from the weight of the earth, it's formed into a type of rock called shale. It's so small the particles are that water barely moves through it, and it's considered, an aquiclude or an aquitard. It doesn't allow water flow from one unit above it to one below it. And again, it really depends on the type of rock and how uniform it is. Rock also isn't flat. It doesn't exist at the same depth from one location to the other. It's usually at an angle. And there can be multiple layers, so you can have different kinds of rock. As you drill through 3 or 4 layers of rock, they could have all of these pretty much. And so it's understanding where the water is available and how permeable your aquifer might be to provide water to your well. Just as another example, if I have the way I describe this is with a horse trough. If I have a horse trough full of sand and gravel and I pour water evenly across the top, and it's dry, you're going to see a wetting front like you do in the upper left. If it's dolomite on the upper right, it's going to go through the fractures. And this is positioned as a simple example looking like bricks, but that's kind of what you have. You have all these fractures and water's flowing through them. If it's crystalline bedrock on the bottom left, that's like granite. The fractures are smaller. They're usually not connected. It depends on where you drill in that unit, how much water you might have and how much might be available. And then the reality is this is still a simplified version. but a lot of times you have multiple layers that you'll drill through when you put in a bedrock well. It's not all just one type of rock, and that's the way our geology is all over the country. So here's another example, and this is from Iowa in their handbook, just showing that at the very top we have glacial drift. So that's, where glaciers have left sand, silt, clay. And there's units along rivers that are sandy. Those are alluvial sands. There's buried units where that used to be a river, the one that's just above the word glacial drift. And so you have small units you can put a well in. But if you get down into the rock, you're going to hit limestone and shale and sandstone as you go deeper. And this might be 1,000 feet. It might be 300 feet. It just depends on where you're at. But some of those act as aquifers and some act as aquatards. So you can see the water level in the deep well comes all the way up into the shale inside the well. That means that sandstone is actually under artesian pressure. So it's under pressure. So the water level in the well comes up above the limestone because it's trying to get to atmospheric pressure. And so that sandstone has some pressure on the system. It's completely full. So is the limestone above it. It's somewhere from either the left or right from this image, the water levels are higher. And so it's pushing the water up in this well. It's really the same principle as if you have a juice box and you put a straw in it. What happens when you squeeze it? Water comes up the straw, and if you squeeze it hard enough, it'll come out. It's the same kind of principle. There's an external force of water pressure making the water go up in that well. As far as where water goes, when we have rainfall, you have recharge areas and you have discharge areas. The groundwater is part of the water cycle. A lot of times you don't show it once it goes in the ground, but it can be only days. This diagram is really blurry, and I apologize. But from a recharge area where it might be sandy and water can infiltrate into the ground, it might seep in a few days. It might take decades to go through to get to the stream, all the way down at the bottom. If it gets through the aquitard really slowly, that 1 foot in 10,000 years, we see really deep aquifers sometimes that you can date, and they are tens to hundreds of thousands of years old, which means, but somewhere, even that very lower confined aquifer discharges somewhere. It's a flowing system. So the water that's there today won't be there tomorrow, so to speak. So about aquifers and wells, it really depends on your geology. Sometimes you have no real aquifer, and in those cases you see a lot of dug or bored large diameter wells, or in the old days it was easier just to hand dig a well. And so like where I lived, where I grew up, which is in central Illinois on a farm, my grandpa didn't know that there was an aquifer at 75 feet. He hand dug a 14-foot well at the base of a ditch, basically. So he felt there'd always be water there, and that was enough supply, unless it was really dry in the summer and someone like me left a hose in our livestock tank, and then we might be without water for a few days. But if you have an aquifer, it can either be sand and gravel or bedrock or both. In some places you may have multiple choices, and the difference there is typically you're going to drill into the shallower unit if it's deep enough to be away from surface influences, because that saves you money. But it may be a water quality issue where either the deep aquifer or the shallower one has water quality issues. We have an aquifer in Illinois where the sand and gravel is pretty high in arsenic, and so you may want to drill into a different unit if you have those choices. And sometimes you don't have any choices. And if you get down into bedrock, that's a consolidated rock well, and it will describe both of those. And again, you might have choices, but you need to understand the differences. A lot of times what I would recommend to people today is many states are starting to put their well logs online. You can see, like in Illinois, there's an interactive map viewer that you can see all the wells around your property and how deep they are, what units they're in, all that information. And that's not the case for every state, but more and more we're seeing that information making its way to the web and being publicly available. So dug and bored wells, these are all examples of what a dug and bored well looks like. So the one on the upper left is an old hand dug well for the farm that's up at the top of the picture. This is one you'd expect to be contaminated. Those posts are worn down by cattle, rubbing on them. You can see on the far bottom right where there's mud prints where they've come up there and done their business. And it's right next to the well. It's shallow. It's covered by pieces of wood and tin and some concrete blocks. Snakes, rats, you name it, can get into wells like that, and we've seen all of those things in wells. It's really just not safe, and they probably need to put in a new well. The one on the right is a typical construction of a 3-foot large diameter bored well. Those tile that are vertical are 4-foot sections, and most of the time they're just laid on top of each other. There's a male end and a female end, and so it's got a groove that one fits into the next, and so water can seep in at each of those grooves. And the problem with that is if it's not grouted around the outside for a distance, then that upper groove is at about 3 feet on this well because it sticks up about 1 foot, and you can have water infiltrating in that at that depth. The one on the bottom left is also a large diameter well, but they've basically taken the one on the right and dropped it down 10 feet or more, and then put a hole in that concrete pad and ran a pipe down through it. And the idea there is that you can put a finer grain material up the upper 10 feet to help protect from infiltration getting into the well. And I'll show you more of that here. So these are both examples. The one on the right or on the left is a well that has a concrete pad on top. And you can see they've added 6 inches of concrete around this down to at least 10 feet or so. And that's a minimum so that those first couple of joints won't have water coming in through them. So water's coming in below 10 feet, which is a little protection. And the other reason you have a large diameter well is because you have no aquifer, you need to store water. And so typically these are 3 foot as a regular design, but we've seen them as big as 20-foot diameter, handmade. But wherever the water level is, you may pump that down during the day or during the evening. Everybody takes showers, or in the morning. And then when no one's home, slowly water seeps back into that well and recovers, and you have that storage. And that's how your water supply works. And that's the other reason why they're large diameter, because you're not counting on the aquifer, you're just counting on the water table, which may be mostly fine material to be able to provide water, and water seeps in slowly. The one on the left is the second example I mentioned. Here they say clean earth fill. A lot of times you'll use clay or concrete, but you put in a regular 6-inch well down to 10 feet, and it runs through that concrete pad, and then it works the same way. And you've basically circumvented having any water come in except below 10 feet there. So sand and gravel well is in a sand and gravel aquifer. So when you put a well into sand, you need to keep the sand out, and that's why these wells have a screen, which is what this image is. The size of the screen, that's a woven single piece of stainless steel. The space between those woven strands depends on the size of the sand. If it's very large gravel, there may be a bigger opening. If it's very fine sand, it may be a very fine opening, very small opening. So what I'll mention is that if you have a 200-foot sand and gravel well, you probably have a 4 or 5 foot screen at the bottom. The rest of the well is solid PVC or steel. So the only place water can come in the well is at 195 to 200 feet below land surface in my example. Everything else is solid pipe. So that's important, because that means anything from the surface has to go through 195 feet of material in order to get into your well, and you're likely getting water just from the aquifer and not anything from the surface. And again, that assumes the well's properly constructed and it's been grouted and all those things. On the other, here's an example of a well, an Illinois well, where they put in 230 feet, number 15 of pipe, and then they have, it doesn't have the screen listed here, does it? Oh yeah, they have an 8-foot section of screen, number 14. That's 12 and 14 slot, and that's a measurement of the space between those slots in the screen to go with their steel pipe. And so you can see the geology here at the bottom of number 18 on the bottom right. It tells you what you're in. You hit fine clean sand at 204, and then as you got down deeper, you hit more coarse sand That's the way, you know, when glaciers melted or in alluvial aquifer along a river, the finer stuff settles last, right? When there's a big water flow, or, you know, it's fairly active flow, the larger particles fall out first and then the finer ones go on top. So in a sand and gravel aquifer, typically the very top of it is much finer sand than deeper. And most of the time the driller is going to go deeper, and so you have less risk of pumping sand, which is hard on your pump and everything else. And so that's the case here. It also has information about, they put in a 15 gallon per minute red jacket submersible pump set at 175 feet. And if you go back to number 17, the static level was 75.5 feet. So the water rose up in the well to 75 feet below land surface, which, even though there's clay at 134 to 204, water rose above that, or actually from 70 to 204, water rose way up into the clay inside the well casing because there's pressure on the system down in the aquifer. And so they pumped it at 15 gallons a minute for an hour. They didn't take a pumping level measurement, which I didn't realize I need to use an example that does. But typically in a good thick sand, and this I know is in the Muhammad Aquifer, which is a very large sand and gravel aquifer in Illinois, the water level pumping at 15 gallons a minute for an hour probably dropped 5 feet at most. And so there's really just a lot of water available in this particular well. Oh, and I guess it says in the remarks here, there was no drawdown available because they developed it by air, which means they dropped an air hose to the bottom, and then the air pushes up the water and it keeps filling that back in, and that's how they clean the drilling mud out of the formation around the well. Okay, so the difference here is a bedrock well. You case them into bedrock, but then below that, you keep drilling, and it's an open hole. Because as I mentioned earlier, water doesn't come from the rock, it comes from fractures. So if you case off the fractures, you can't get water in your well. So the rock itself acts as the casing. And in this example, you can see they had some overburden, which is, you know, clay, silt, sand. And then below that, they went 10 to 20 feet into the casing into the bedrock. So you seed it into the rock so that it's solid. And this is after the hole's already drilled. But then you keep drilling, you're trying to hit fractures and find water. And depending on how many fractures you find, you may have a lot, you may not have that much. But the thing to understand is if you have a bedrock well, you need to know how much casing you have. Because we run into wells that are older, that don't meet code today, that were installed, and maybe bedrock's only a few feet below land surface. They may only have 10 or 15 feet of casing. And after that, anything can get in the well. And so it's likely if you have fractures that shallow, they're going to come to the surface. And so your water could be, it's more of a chance. Or if you only have one fracture, it could be coming from very far away, you know, as far as a mile away, to fill your well. And so it's good to understand those things. And the best example I can give, the same 200-foot well, if it only has, it could have 20 feet of casing, it could have 200 feet of casing. 200 is a lot better as far as protecting from surface influences. So it's important, again, to understand your well, the geology, and all those things together. And here's a bedrock well. It's also from one from Illinois. And if you look down at number 18, you can see they hit broken limestone. They had sand. They had 12 feet of sand, and the driller chose not to put in a well. Some drillers only drill bedrock wells. Some will do either. And I know there is a driller in Illinois who will blow right through, 30 feet of sand to put in a bedrock well because he doesn't like to deal with well screens and those sorts of things. That's unfortunate, is all I can say. But if you have, in this case, at 187 feet, they hit broken limestone, which the top of it's kind of fractured, and then they went through 68 more feet of limestone bedrock. So what they did for that well is they put in, if you look at number 15, from the surface to 179 feet below land surface, which were still in sand there, they put in PVC. But for the lower 20 feet, the first thing they put in is 20 feet of black steel. And that is seated in the bedrock 10 feet. And they use steel because they can really crank down on the seat on that to get it solid in the rock, and so it won't move. And then they connected it to PVC for the rest of the service, and that's really to save some money. But it's really interesting how all this works. And in this case, the static water level is 130 feet, again up into the clay and sand and boulders. in the unconsolidated material, and they pumped it at 25 gallons a minute for 2 hours. It dropped to 160 feet. Well, they've got a 260-foot well, and their pump set, where was their pump set? I forgot what they said here. Does it have a depth of the pump? I'm not looking at my own information here. Anyway, 160 feet. And so they reached the pump, pumping at 25 gallons a minute, but in the end, they installed a 12-gallon per minute pump. And typically, a driller will do that. They'll put in a larger pump than they plan to put in the home. And most times, and this is not for a home, this is for a camp. Most homes have a 5-gallon per minute pump unless you have another reason like livestock or some other things you want to do. But they pump it harder than they're going to, so they are sure when they put in the sized pump for your property that you're going to have plenty of water, or they know that in advance. Sometimes, there's wells that only, I mentioned, pump 1 or 2 gallons a minute. When they try to pump this and they figure that out, then they'll come up with an alternate solution for you, which may be putting in a 1 gallon per minute pump. And like one of the cases in Colorado I mentioned, they actually put in a 3,000 gallon cistern enclosed, and they pump their well into the cistern and then pump from the cistern into their home. And that's so that during the night or when no one's home, the well can continually basically pump a gallon a minute, so that when they get home and they need to use water, they have enough in the cistern to actually do that. It's really same concept as a large diameter well. You're storing water that you just doesn't come in as quickly as you need it. And so it really depends on your situation and where you live in those cases. So there's lots of issues related to private wells. The most important things are public health protection, source water protection, and the water quality in the aquifer itself. And so I want to mention that because you have all these issues that are in the news. We had Flint, Michigan, and it raised all these questions about lead. Right now it's PFAS chemicals. There's always things in the news. But what we find, even I mentioned boil orders here because we've had community water supply operators who've told us they put out a boil order for their community water supply, and they'll get calls from private well owners in the area asking if they need to be concerned. And honestly, that's a lack of knowledge of the well owner. A boil order is issued when there's a break in one of their service lines, so that it's not sealed and it's not necessarily under pressure. And if it's not, it can allow stuff to come in through that break in the line, and that could mean bacteria or other things, and they have a responsibility under the Safe Drinking Water Act to tell people to boil their water to make sure it's safe until they can get that fixed. It has nothing to do with the aquifer. It has nothing to do with the private well. It's really about their distribution system. And I bring all that up because this happens quite a bit, these kind of things. And so what we really find is we could eliminate a lot of issues related to private wells and drinking water quality if we could correct poor construction. I'm showing 2 examples of old wells that are still in use today, and we could raise the level of knowledge of well owners. And that's our goal, is to work on that bottom one as much as we can. The more you know about your well, how it works, what your geology is, what your potential problems might be, the better you're going to be able to deal with an issue you might have. You should sample regularly to be sure your water's safe, all those things. It's estimated that 2/3 of well owners have never tested their well, and that's on you as a well owner. It's part of having a well. We have folks who want to live off the grid and all those things. You don't know what you're drinking if you don't get it tested. You have to do all those things in order to ensure a safe water supply, or add treatment to make sure that it's safe. But it's a more expensive option to add treatment if you haven't tested it. And we give that advice a lot because a lot of people tell us they have this problem. And the first question we ask is, have you tested? Well, no, you got to test first to know what's going on. So as far as correcting poor construction, every state has well construction code except 2. And those codes change as new information becomes available and as science improves or whatever. But there are many wells out there. So in Illinois, it was 1968. In New York, it was 2000. I think Nebraska was 1982. So it really depends on your state and when they enacted laws. But in every case, if there was a well already in existence, it was grandfathered in. It didn't have to meet code. And so we still see a lot of wells in pits today, which are dangerous for a couple of reasons. And there's also many hand-dug wells still in use, including the one I grew up on. So they provide not only an opportunity for surface contamination of your well, but even the aquifer, and they're also, especially wells and pits, are a safety hazard. They just are. So this example from the Washington State Department of Ecology, which is the state organization that regulates drillers and well construction code in Washington State, has a blog. They put this information up. There's several good blog stories from them. They have a piece of plywood. This is a little well house, and you can see the well, and it's got a surface pump here. But that piece of plywood, the woman who lived there stepped on it, broke, fell through, and it killed her. And so, but if you look at this, it looks like all that gray matter that's by the funnel is probably rotting insulation from the sides of the well house. And I'm sure there's a lot of that floating down in the well. Mice can get in here, fall in, all kinds of things. It's just not the way to have your well. It's just not safe. Yeah, to me, this would all need to be redone. And the picture on the right, this is a well that actually isn't in use anymore. But on the farm, this is, you can see that's a dead goat. And below the concrete tile that you're seeing there is old pieces of rock. This was an old rock well from Southern Illinois that was in use back in, like the early 1900s. And so, but they put this concrete tile, 4-foot tile, and it's only sticking up about half a foot, and they left it open. And somebody's livestock got out, and their goat saw that water, and that was it. And this was found obviously well after the goat fell in the well. But we see frogs, snakes, rabbits, you name it, in wells. And you should not have a well that has an opening big enough for something like that to get in your well. If it is, you need to consider how to change that, because that's really the problem to start with. We see even drilled wells with a 4 or 5 inch casing with an old rusty Folgers can sitting on top of them. It's just not protective, and it matters. So bring your well up to code if you can, and you can afford to. And if it's in a pit, that would mean extending the pipe up to land surface, filling that pit in. The reason you have pits, well pits, in a well down at 4 or 5 feet is because before the 1960s, there wasn't a pitless adapter, which was developed to change that whole approach to installing a well. So in northern climates where you have a frost line, you couldn't run your pipes all the way to the surface through the top of the well because they'd freeze in the winter. And so that's why you had your well down in a pit. It would never freeze there. Then they invented the pitless adapter, which has an elbow in it that sends the water to your house at 3 or 4 feet, that allows you to have your pipe all the way up to the surface. And so that's what you really need to install if you're in that sort of situation. But there's a lot of local folks you can talk to, your county health department, county extension. If there's a local well authority, some states have those, or regional, or your drilling contractor, and find out what they recommend. And ask 2 or 3 people. Don't just go on one person's advice necessarily, especially if they have a stake in the game. You should find out the best approach and do your homework. Same thing with abandoned wells. So a lot of people like to buy a property with an old farmhouse that's dilapidated or already been torn down. They build a new home, put in a new well, and a lot of times there's an old undocumented well there that no one either knows about or they mention it, but it's not a part of the issue. I work with a lot of farmers, and I'll go to a property and there's 3 or 4 wells on the property going back several generations. And they still try to use some of those sometimes, either for their livestock or whatever. But all those old wells, you forget about them, or someone, you sell the property, those are a safety hazard. And, if someone gets hurt or falls in a well, whether they're trespassing or not, you could really be in trouble, be responsible if they get hurt or if it contaminates an aquifer. The other thing we see is those holes in the ground make a great garbage disposal for some people. They think out of sight, out of mind. We helped with a well sealing of a dug well, and when the driller opened up, took this concrete pad off, down in the well, it was only 22 feet deep, there were literally about 10,000 cigarette butts and several lighters. And so the person who'd owned the property before would walk out his back door to smoke, and there was this concrete pad with a little 3-inch hole where the old hand pump used to be, and that was his ashtray. not very smart. It just and that well wasn't in use, so it wasn't as such a health hazard, but it's just an example of what happens. And so again, with old abandoned wells, here's two examples. Again, both of these are from the Washington State Department of Ecology. They're pulling a horse out of an old abandoned well, and a guy walking in his backyard fell down 45 feet into the well, and he walked away from this. Very lucky. So, and the newspaper clippings here, 3 of these are from Illinois, and I used to use this because, back in the day, when the internet wasn't quite as prevalent, you got all your news from the newspaper. Well, I guarantee you the people from Springfield, the bottom one, and from Buffalo Grove, which is a Chicago suburb, the second one, and Galesburg, which is in western Illinois, didn't know that the other ones happened. But people get killed in these old wells. And the third one down is Jessica McClure, if everyone old enough to remember. It was carried live on CNN as they tried to get her out of a well. I think it took a day and a half or so to dig her out. And it was covered live on CNN on TV and captured the nation. And now she's a mother of 3. Yeah, it's just, it's interesting how such a common thing is so overlooked. Okay, so a little bit about aquifers. An aquifer is a saturated bed, which means, so again, if it's sand, it's got water in between the sand grains, or if it's bedrock, the fractures are full of water, which yields the water in sufficient quantity to be of consequence as a source of supply. This is a really convoluted definition. I won't say convoluted, that's the wrong word, but a lot of people struggle with what's an aquifer and what isn't in the scientific field of groundwater, because if you only need 5 gallons a minute, and it might be an aquifer, but if you're a community that needs 300 gallons a minute and it won't provide it, then it's not necessarily an aquitard, but it's not really an aquifer either. And so that's why this definition is the way it is. But basically, it's a source of water. It's a geologic unit that can provide enough water. Not only does it store enough water, it's porous enough, but it also has enough permeability that water can go towards the well when you start pumping it. So, water flows based on pressure. So when you start pumping a well, the water level in the well drops the most. And then the water in the aquifer around it also drops in a cone shape called the cone of depression. I'm getting ahead of myself. But it's no different than whenever you take the plug out of the end of the bathtub. The lowest point is where the drain is, and you can see the water swirling and circling. So all of that is about how fast water can flow to that point. And in a bathtub, it's because there's no resistance, right? It's just water flowing in a tub. But if you filled that full of sand or different material and tested how quickly the water would run out, you'd see differences, and that's kind of what the point is here. And an aquitard is more of a clay or a solid rock or silt. Or it could even be mixed with very fine sand, but it doesn't provide enough water to a well. Or does it provide enough leakage where water is going to fill back up again quick enough into a well? My point before was different users will define what an aquifer is or isn't, depending on what their need is. So you can have 2 kinds of aquifers. They're either unconfined or confined. And an unconfined aquifer means it has a free surface, so it's not saturated all the way through. And I'll show you this in a minute. And so the free surface is at atmospheric pressure, and that's the water table. There's a water table everywhere. It doesn't mean it's a water source. We have a lot of clay. The upper 20 or 40 feet of geologic material in Champaign County is clay. The water table is at about 5 feet, which means that clay is saturated below 5 feet. Just because it's a water table doesn't mean it's an aquifer or it can provide enough water. So there's a difference there. It's just where the water becomes saturated from the surface, and that's that free surface at 5 feet is at atmospheric pressure. So a confined aquifer is it's confined by pressure, and so it can water levels can rise above the top of it if you put a well in it. And so it obviously can't rise above the aquifer if there's an aquitard above it, but when you punch a hole in it, water comes up like it does through the straw I mentioned earlier. And this can be is considered an artesian aquifer. Artesian doesn't mean it's flowing out the well. Flowing well is an artesian well, but you can also have an artesian well that doesn't flow, If it's just higher than the aquifer, that means it's under pressure. So here's a water table situation. This whole thing is sand until you get to bedrock at the very bottom. You have a water table, you have two different wells at different depths, they have the exact same water level measurement because it's all one unit and water can flow freely through the sand. Okay, but if you have an aquitard below the sand and then a confined aquifer, it could also be sand. They may have different water levels because the aquitard doesn't let water flow through the same way, and they may have different water sources off to the left or right. Water is always flowing, as I mentioned. Both of these aquifers have a flow direction. They're flowing towards a discharge point, like to a river or a stream or the ocean. So they all are moving. Which direction is flow? You'd need more than one well to figure that out, because water goes downhill. So as you get closer to the discharge point, the water level in this confined aquifer would be a little lower than it is at this well. But this shows that there's a difference. There's two different water levels here. The dashed line that's up in the confining layer is the water level in the confined aquifer. And it's at that point it stops rising because it reached atmospheric pressure. So the weight of the atmosphere pushing down on the water is equivalent to the pressure that the aquifer can insert trying to push it up. Okay, so this is a confined aquifer again, so it's the same as the last one, except this has got this dashed blue line is showing the water table above. It's really irrelevant in this case. The water level in the confined aquifer is where the top of where the little triangle is, the black triangle. And so you can have, it can be lower than the water table, it can be higher than the water table, or it can be flowing, right? And that's a flowing artesian well. So it really, it depends on where the water's coming from horizontally. In a lot of cases, the recharge from above, there may be a little water seeping down through the confining layer into this aquifer, especially when the water levels are lower in the confined aquifer. But in this particular case, at the top of this confined aquifer, water is slowly seeping up into the confining layer because the pressure from below is greater than the water table pushing down. So here's another example. You can kind of see the gray is where there's water in each of these wells. This diagram isn't great because it just uses lines, but if you can see there's a water table aquifer, upper confining bed, which means it's an aquitard, then an artesian aquifer, and then a lower confining bed before you get to rock. So the dashed line is the water level in the artesian aquifer. And because geology is not flat, up on the upper right is where the recharge area is, where that aquifer comes to the surface. So water can infiltrate directly. So it's moving down through the aquifer. And if you put in a well, it's going to be artesian, like the furthest right well is artesian because it comes up above the confining bed, but it's not up to ground surface. Whereas if you're in a lower point on the landscape, like near a stream, that same aquifer, you can see the dashed line goes down to where the well is because water's coming out there. But the natural water level would be above land surface there if it could just freely flow. And so that's just how it works. And the whole time the water table aquifer is a solid line, and it's at a different, it's lower. So water's always being pushed up. Here's another real world example, so to speak. This is in Illinois. The blue on the right is the Lake Michigan in Chicago. And if you go straight west of Chicago in the northern part of the state, you get to DeKalb. It's about 50 miles away, I believe, and another 30 or 40 miles you get to Rockford, where this St. Peter sandstone actually comes to the surface. So the recharge area for the St. Pete sandstone is over by Rockford, 80 miles away, and so water's coming down because it's at a higher, going from a higher water level to a lower water level. Well, the reason it's lower is because we're pumping here. So each of these communities, and there's a lot more, pump from both the St. Pete sandstone and the Ironton-Galesville sandstone, and their wells are open in both formations. So they're pulling water out of both of those formations, which lowers the water level in those wells, which makes the flow change. So if there were no wells whatsoever, all the flow would be from left to right. But since there's pumpage, they've lowered the water level in the middle. And so you can see on the right side, those arrows pointing back to the west, the other way, or to the left, water's flowing from both directions. That's not sustainable long term if they're pumping too much water. And there's an issue in that Chicago area now because of that. So it's just another example of how water flow, it's based on pressure, not what's flat, not what's higher than lower. It depends on how hard you're squeezing the juice box, and that's or pulling water out. And as far as these are really old figures, but they're so great, I always use them. This is a water table aquifer at the top, and I mentioned a cone of depression, so that's what this is. When you pump the well, the water level's lowest at the well, and everywhere around it, water's trying to come back and fill in. Just like, if you start sucking on a straw, you don't, the hole, it's small enough in a cup that you don't see it, but it's actually just a little bit lower right at the straw than it is surrounding it, and water's moving into the middle to fill that space in. So the bottom figure there is elevation. So the pumping well, they've lowered the water level to an elevation of 400 mean sea level, where the static level before pumping was turned on was at 460. So this is an idealized case where all the sand's uniform and they'd be perfect circles. That's not what we see in the real world. Aquifers aren't square and totally extensive. Sometimes they're very thin, and so some of those things change, but this is how it works, and water's flowing into the well to fill that back in. And unless you pumped it hard enough to basically take all the water out of the aquifer near the well, you're going to continue to have flow towards the well. Here's an example of two wells and how that would look. The two wells kind of interfere with each other between the two. There's not as much water to recharge back towards each well, and so you see lower water levels in the middle. So communities, when they have to put in multiple wells for a well field, they look at all the porosity and permeability, and a lot of times they'll even model what will happen when they pump it, so they know how far to space the wells apart based on the conditions of the aquifer and those properties of the aquifer. And if you're near a boundary, the edge of the aquifer, it obviously can't put water back in on that side. And so you see here it goes down to 400 again, but you have, it's disproportionate in different directions if you look at the top, where drawdown is. And that might only matter if there's neighbors' wells nearby. We see problems when there's an irrigation well in a rural area and a lot of private wells. Sometimes the irrigation wells will cause a private well to go dry certain times of the year. And the opposite occurs if you're near a river. If the river is directly connected to the aquifer, then it's a source. Whenever you start pumping the well, water from the river is actually going to help contribute and fill in, and it's a much more constant water source. So it's basically a constant water elevation head of 445. And so it's going to minimize the amount of drawdown on that side of the well because of that. So, and that's called a recharge boundary. So, and it basically means they're a lot more likely to be able to provide, have a lot more water available with less drawdown than an area that's away from a river. I'm just going to quickly show you our State Geological Survey's interactive map. I mentioned a number of states have these now where you can look at the wells that are available. It doesn't mean your well log will be there. In Illinois, we started requiring well logs in 1968. We're fairly ahead of the game compared to many states, and yet we probably have about 60% maybe of the actual wells in use. We estimate about 750,000 wells in use, and this says our paper records archive for over 700,000 wells. Those aren't our water wells, and many of them are abandoned. There's records for about 450,000 active wells in our files. And again, the Water Survey and Geological Survey are sister departments or divisions under the Prairie Research Institute. So we work together on all these things, and yeah, we coordinate all this work. So this is Champaign County. When you zoom in, you see all of the wells, and when you pull up this tool, and if I zoom in further, I can click on a well, and it shows me where there's a little side arrow coming out of that box right about the middle, and it shows me there's 3 wells listed there. And if you click on the API number, this is near Willard Airport, which is not far from where I live, and you can see the geology of that particular well. Now this is a generated log, it's not the actual well log. The ones I showed you before were actual logs that the drillers filed. The GS actually puts all this information into a database, and then they generate these. But you can also get to the original log by contacting us, or In some cases, we've started putting those in here as well. So like in this case, this is a 169-foot well, and the blue imaging down here that says image viewing help, there's 3 water survey documents related to this. One of them is actually the log. And so we've scanned this and it's available, the same 169-foot well. And you can see this was filled out by a well driller when they put in the well in 1968, it looks like. And so in our shop, we used to be separate agencies. We designate every well with a P number, which is down the bottom left. And we have a system here that we can find those for folks. And if you have the API number, we can also then use that to get to the well log and give you the original log. It has more information on it. Sometimes there's additional sheets, like that one had 3. I don't think I included all those. But so that's what I have for groundwater and wells today. Just some really basic information and giving you some tools, hopefully. I do want to talk about our private well class. What we find is that when we ask people on our webinars, have you taken our class? A lot of folks think that the webinars are the class. They are not. It's a 10-lesson class. It's sent to you over 10 weeks. It's self-paced. You sign up on our website with an email address, your first name, and what state you live in. And that's really so that we can show to US EPA and Rcap that we're working with well owners in every state. And then it sends you a PDF once a week for 10 weeks. It's much more detailed. The entire thing is 86 pages. There's 10 lessons, as I mentioned, and it's much more comprehensive, and it's meant to really help you understand how to take care of your well. This is our front page, privatewellclass.org. Again, you can click on Take a Free Class. That takes you to, well, there's also under Resources. For each of the lessons, they're 6 to 10 pages long. It may not resonate with you. They're written in a way like someone's talking to you, and some people that doesn't resonate with. And so there's all these other resources, like for lesson 1, that you can, these are all free and publicly available from other sources that talk about some of the same concepts and issues. I know the 2 documents from Raymond Lyle, we've actually used some of the information from his bulletins. They're really well done, and they're really explain things in a clear, common way that make them easy to understand. But for each lesson, there's one of these, so there's 10 of these little resource libraries that have information to help you with concepts that are in each of the 10 lessons. So we also do videos like the one we're doing today, or do webinars like the ones we were doing today. This is last month's. It was on November 18th. It's called Well Care 101. We record those like we are recording today's, and we put them up and make them available. And I'll get into it more. Well, I'll just mention at the end of today's webinar, or probably in about 10 minutes, we're going to start answering the questions you all asked in advance when you signed up for the webinar. Every month that's different. Now, some questions we get asked a ton of questions every time. How to disinfect my well. So it's probably in most of them, but there's also really different questions about different topics. You'll see as we get into this, at the end of each webinar, we do the same thing. So what's really valuable to you is, there's probably 10 of these Well Care 101 videos because we've done the webinar a couple times a year over the last 5 or 6 years. But at the end, the second half, the questions may be different, and they're worth your time to go back and look through if you want to really learn more about your well or other people's problems, certain situations. We've had some really odd questions and some really common ones, and we'll get to that in a minute. But I want to mention that we do that for every webinar. We try to answer some of the questions you all provide, and by doing that, there's some uniqueness in each one of these, and there's information you can learn from. So we do a septic systems webinar every July. The last one was July 20th in 2021. Again, septic systems are a big part, and management of septic systems are a big part of being a private well owner. You can cause a lot of problems if you're not pumping your tank and maintaining it properly. It can ruin your septic field and not only cost you a lot of money, but also cause contamination problems in the shallow area around your home. And so it's just really helpful information. I'm not a septic expert, so one of the Rcap folks that I work with, who's in Massachusetts, he was a sanitarian for 8 years, and his name's Jim. He's been very gracious, and for the last several years, he's come on and answered a lot of the questions that people have. I know just enough to be dangerous, is what I'll say about septic systems. We also do kind of one-off webinars. We did one in 2020 about funding and financing. there aren't a lot of resources for funding or financing private wells, but if you're low income, there are some sources through USDA. There's also the Water Systems Council has a separate organization they help maintain. Oh my gosh, I can't think of the name of it. Anyway, we had those folks come and talk about the USDA loan program, and we talked about a lot of different resources that are available. Just like in some parts of the country where septic issues are more watershed problems, there are resources available locally through either a soil water conservation district or some other unit where you might be able to get help, or even for abandoning wells, or in Iowa has a grants to counties program where they may help with sealing an abandoned well, or the county can also help pay for sampling costs. And so it's worth going through that particular webinar to look at what all the sources are and give you some ideas to start looking locally and see if there might be some help. And on things that come up like lead. We again brought in an expert, Dr. Kelsey Piper, who was at Virginia Tech at the time and done a lot of lead and private well type research. I'll just say that it's really lead in the home that's the problem, or in the well itself from the pipe materials. It's not lead in the aquifer. And so there's a lot to understand about, depending on how old your home is and the chemistry of your water, whether that's a risk to you or not. And that's, again, worth going through those videos, those little webinars. And like for lead, we created a source page. It's just privatewellclass.org/lead. And the idea there is we put up information, like water filters. EPA came out after a lot of the work, things that happened at Flint, and they had done some investigation of some of the filters and which ones work best and things like that. And so you can find a lot of information in these resources if you're concerned about lead in your private well water. I will say though, what's the first thing you should do? If I was doing a quiz right now, to understand what your issues are with lead, sample your water, right? And with lead sampling, you do two samples. You do a first draw from your kitchen tap, and then you let it run for a little bit and do a second sample, and there's details for that if you need to know. But your lab or county health department can give you that information too. We have some, this says 16, but there's actually 22 little training videos. This one, for example, is what to know about a shared well. I've worked with private well owners for over 30 years. I had no idea there were so many shared wells around the country, but it's really common, and it leads to a lot of problems. Friends who aren't friends anymore, neighbors who become enemies. There's a lot to being a shared well owner, and we see a lot of these cases where there's no agreement, there's no legal standing, and all I can say is if you're sharing a well with someone else and the well is not on your property, you want to have some kind of legal agreement, because all it takes is for a pump to fail or for some other issue to happen with a well, where everybody's got to pony up some money to fix it, and it can ruin a lot of relationships. So it's really good to understand those things. And pressure problems, we know a lot of private well owners have pressure issues in their homes. One of our videos, it's called How Does My Pressure Tank Work?, has had over 400,000 views since 2016. And that's just because people want to know about their wells and how their water system works, and may not have their pressure settings right, or not understand that if they have an old air style tank that can become waterlogged and you have to take care of it and all those things. We started a podcast. It's called the Drinking Water in Rural America podcast. It actually, there's 12 episodes. This is a snapshot I took after the fourth one. But we had Judy Manners come on. She's from Tennessee Department of Health, and she's a springs expert and has done a lot of work looking at springs in Tennessee. It's really an eye-opening presentation that she gave at her 2017 private well conference. So we had her on to talk about that on our podcast. But there's 12 of these are out now. They all been published for this year, and we'll do another set of 12 next spring. And it's really, I guess it's geared not as much for a well owner as it is for professionals, because it covers both the private side and the public side. So I know we have a state administrator talk about using chloramines as a disinfect, or as a treatment instead of chlorine in community water systems, and a few other issues we've talked about that are more public water supply. We have a sister program called wateroperator.org, and we provide support to systems under 10,000 people, water and wastewater systems, and that's really where this thing kind of ties the two together. But it's interesting. If you're into podcasts, they're probably worth listening to. Our entire class is available in Spanish. I won't say more about that. Let us know if you have Spanish-speaking well owners in your area who would prefer to take the class in Spanish. There's also some of the videos, not all of them, have been converted to Spanish and are available through this website. And the goal, as I mentioned earlier, I think the goal of our program is really to help well owners learn and be more informed well owners. And the more we can give them education and outreach and advice, they need to understand why their well is important, why they need to know how it works, and so that they can better protect themselves and their family from any kind of risk relate to being a private well owner. And so, go through our class if you haven't taken it. If you need resources, if you're a professional, a lot of our slides and stuff I make available to people because, again, as I mentioned, there's a lot more well owners than we can ever reach with one different project or one group. And so we try to share what we have and want to work with whoever's willing to work with us. The other problem I think we have is we don't have a consistent message from one area to another or from one local jurisdiction or state to another. You see materials that are a little different on the same topic from state to state sometimes. And the more we can share material and make it more consistent, so we're giving the same message to well owners day in and day out, the better it'll be for all of us and the more encouraging I think it'll be for well owners to learn. So we're going to get to our questions. We did get a lot of questions. We can't answer them all. And so especially if you just signed up in the last day or two, they probably won't get answered today. We try to look at these a few days in advance and be prepared for today. And so they're part of the slide deck that we send out. And again, if you have any questions that don't come up or that you have already, you can put them in the question box or the chat box. And Katie's making a list of those. And it doesn't look like we have any questions yet, so that's okay. Okay, so groundwater under the influence. So what is the typical treatment for a shallow well where the groundwater is under the influence of surface water? Is it safer just to haul water? Well, for those of you that aren't familiar with public water supplies, there's a designation called groundwater under the influence of surface water. And if your well, even though it's a groundwater well for a community water supply, potentially is influenced by surface water, you have to treat it like it's surface water because it can have bacteria, viruses, other things that you find in lakes, rivers, streams. And so what well owners do, and this also includes springs, right? We have a lot of natural springs in the country that folks use as their water source, and those are also considered surface water. And so what we recommend for that is you just need to continually disinfect. You can't just take a sample and find coliform and decide you're going to shot chlorinate. You actually need to have a disinfection system so that all your water is being treated like a community water supply is before it comes in your home. And there's really the two common ways to do that are continuous feed chlorination or UV ultraviolet light. And the UV industry has really grown and come down in price commercially for smaller systems like private wells just because there's such a need. And so they're much more common, again, in Southern Illinois, Indiana, Kentucky, Tennessee, as well as other areas that maybe karst and have a lot of springs. A lot of people complain about the taste of chlorine. And so if you want to disinfect and not have chlorine, you can always use UV, but you have to do one or the other or you're putting yourself at risk. Because even though right now you may be used to whatever bacteria it is that are coming from your well, I grew up on a well that wasn't safe and I was used to it. I might have got sick when I was little a few times, I don't know, but I could drink our well water and not get sick. But I went to college and was gone for 4 months, drank community water that had chlorine in it. All the bacteria that were in my stomach my whole life disappeared. And when I went back home for Christmas and tried to drink our well water, I got sick. And so I could no longer drink our well water. And we see that all the time. People are like, well, no one's gotten sick. I never get sick from this water. Well, you can develop a tolerance for the certain bacteria that you might have, but you drink somebody else's or you stop drinking it for a while and come back, or anybody comes to your home, it can make them sick. And so you need to have continuous disinfection. And so, yeah, that's just the way it is. Water's like any other thing in the ground. Some people have it, some people don't. Some people have really good water, some people have really poor water quality. And so it can usually always be taken care of with treatment if you know what you're looking for. And so that's the thing to understand. So what do you test for? We get asked this a lot, and so we have a list. I do want to say it's different. It depends on how deep your well is. If it's really deep and it's screened, or if it's solid pipe and it's got a good unconsolidated clay material at the top, where it's very unlikely that surface contamination is going to get in. It's well grouted. All those things. And when I say known contaminants in an area, there are some odd drinking water contaminants that you might only find in a few places. And if you're in one of those places, you need to test for that. And the only way to find that out is to do a little research. So ask your local, and I must have used this from another talk because it says Louisiana in here. I apologize for that. But ask your local county or state health department, extension. They should have an idea of what you have air water quality. Even your USGS or your state water resource agency, whoever makes water quality maps of your state may be a different group than your health department. I know, we do that in Illinois, and we're not part of a state department of health. And so find out, you can just Google water quality maps for Illinois, and you'll get several agencies that pop up that may have some of that information. And I guarantee if you call one of those folks, if they're not the right person, they'll know the folks at the other agencies that would be the right person. So you just need to ask, I live in this county, do I need to be concerned about arsenic? Or what should I be concerned about? Are there any known contaminants in this area? Somebody can look that up and help you. And again, extension may help you as well. So what we recommend is you sample for coliform and nitrate annually, not because they will make you sick per se. Coliform, E. coli is obviously bad. Coliform is an indicator that you might have other things. Nitrate, it's on the Safe Drinking Water Act list because of for babies, for blue baby syndrome. There's some evidence that suggests it may have other water quality issues, but it's not on the list for that. EPA hasn't identified it as a contaminant for adults. And so you might be drinking water with coliform and nitrate and it hasn't bothered you at all. But if you have coliform or elevated nitrate, it means that you have a pathway into your well. And this is really only a test to look at well integrity. It doesn't mean, I've so many people say, well, I tested my well for coliform and nitrate. They said my well was safe. Well, it means your well isn't contributing to potential contamination because it's not properly installed. It doesn't mean you don't have arsenic or radon or some other contaminant that might naturally occur. You still have to test your well for all those things. And here's a perfect example. This is Rhode Island. All the little dots are where there used to be orchards, where until the 60s, arsenic was used almost exclusively as a pesticide in orchards. And so now in all of these areas, they've identified soil contamination. And in a few of those, it's seeped into groundwater and causing groundwater contamination. And so they've listed them all on this map to tell you as a Rhode Islander that if you're near an orchard, you might want to test your well for arsenic. So, but the interesting part here is that big splotch in the middle. About a third of Rhode Island has high beryllium. And I tell this story almost every time I show this slide, but I had no idea beryllium was a regulated contaminant, and I'm sure most of you didn't know that either, because it's not something you hear about very often. But it is. It has health effects. It's part of the it's a primary contaminant under the Safe Drinking Water Act. And if you're in Rhode Island, you should be concerned if you live in this area, and you should test for beryllium. And I don't make that recommendation to anyone else in the country. Now, if you contact your local health department and they tell you that beryllium might be an issue, then you'd want to test for it. But that's why you need to ask, because you need to know what you're up against as far as, if it's possible, you should test for it. if it's especially a natural occurring contaminant like this, there's no doubt it's there. Similarly, Massachusetts DEP has this site where if you have a bedrock well, you can put in your address and it'll tell you if you have risk of arsenic or uranium or both. That's pretty nice. Be able to, they've already looked at that enough, have enough samples that they basically mapped the state with arsenic and uranium issues. And now you can just type in an address and tell you if you're in that area, we have to be concerned. And Wisconsin has one of the nicer tools. This is an interactive map. So I got on this website, I told it up in the right corner, I wanted to look at arsenic by county, and what it's showing me are areas in the legend there where it's less than 5, 6 to 10 through greater than 21. The health standard for a public water supply under the Safe Drinking Water Act is 10. So every community water supply can't serve water to their customers that's over 10 ppb. And these red counties, the 3 near Green Bay, are over 21 on average. Now, this site's changed since I took this screenshot. There's some counties here that are clear because they didn't have any data, and I believe it's all filled in now. And actually, where these areas are has changed a little bit too as they get more samples. So it's a living document, if you will, in that it's a growing database. But if if I was going to move to Green Bay for a job and I wanted to buy a house in the country, having a tool like this to know I wouldn't buy a house without first getting it tested for arsenic, or talking to the well owner and the homeowner if they've added arsenic treatment. What we tell homeowners, whether you're going to buy or sell, is it's best to do it all in advance, so that you can, if you have an informed person trying to buy your home, you might lose a sale. It's better just to deal with it than to let it go and hope for the best. So it's a really nice site, though. You can look at a bunch of different contaminants. And more states are starting to do this kind of work, or put more of their water quality data online as just an overall map. New Jersey passed a law probably close to 20 years ago now where they require every home sale to have a test by the state lab for a property that has a well. And because of that, they have now about 260,000 samples of private wells in New Jersey. And they plot all that on a map and make it available, but they don't do it individually so that it doesn't affect an individual home sale per se. But you can see where there's high arsenic or low arsenic or high whatever, and that should inform you if you're going to buy a home with a private well, what you need to look at and what you need to test for in advance before you buy that property. Because it's really buyer beware. That's the one thing I'll say. So what we suggest is, again, test for coliform and nitrate annually, and this is for a national audience. And then you test for the things that are listed here. It gives you a good idea of the overall chemistry. If there are issues like, with turbidity, or if the pH is really low, that's a sign of, could be a sign of corrosivity for lead or copper issues. If you have copper pipes, you should test for copper. I had someone just last week call me and say they had, their water tasted kind of metallic. Well, they need to get a test done, and they do have copper pipes, and that's probably why. And so they're probably leaching a little copper, which is, it's got health effects. It's dangerous. You don't want, it's a heavy metal. So anyway, besides this list, and this really, even gives you an idea of the overall chemistry, then you should also talk to your local state health department or other agency that deals with water quality to understand if there's anything in addition to this you should test for. Okay, so how can I know if my well is impacted by my neighbor's septic? Well, test first. If you haven't tested, you don't know if you have any problems at all, and maybe you have, it wasn't listed on the question. But if you have coliform or elevated nitrate, and I botched this too. So if you have coliform present, then the next step would be to chlorinate your system and retest after that to ensure your system is free of bacteria. And if it's nitrate, then you need to probably add treatment. There's treatment for nitrate depending on your situation. And I talked to a treatment professional about that, as well as your health department. Determining the source is a little more tricky. Having your well log where you know how deep your well is. You could probably even, like in Illinois, I could find my neighbor's well log if I wanted to. What's the distance, groundwater flow direction? There's a lot of things that you could do to investigate that and look at it. And if it's a shallow well and your neighbor's well is shallow as well, then a lot of times, the water table kind of follows the landscape. So for instance, if you have an old dug well like the one I grew up on, and you have septic systems that are further up gradient, say you're in even a rural subdivision where all the houses on one end are near the lake and on the other end are on an upland, and there's a road that runs up that hill, well, all the septic's going to run down the water table towards that lake. Even if it's been broken down and all those things, if your well's shallow and it's between that, then that's evidence that there's potentially a problem. But again, you need to sample first, and after you retest, if you still have coliform, and if you have coliform at all, in between that you need to boil your water, right, until you can get a clean test. And if it doesn't take care of it, there's multiple reasons for that, and I'm going to answer that question in a few minutes. So hang on for that, because shot chlorinating your well is not a simple thing, and so if you shot chlorinate it and you still have bacteria, there could be multiple reasons for that. So yeah, hopefully that answers your question. So our aquifer is most likely shared with neighbors. I'm sure it is. If water tests fine for bacteria, and if their water tests fine for bacteria, mine does not, what could be the cause? Well, it's typically not an aquifer issue. Bacteria doesn't travel through an aquifer. It only lasts it only lasts a little while, especially coliform and that stuff. The bacteria that exist in groundwater that are ubiquitous are like sulfate-reducing bacteria and iron bacteria. They can be anywhere, but you don't see coliform E. coli staying that long. It's not like they just exist, so it's not really an aquifer problem. It's most likely that your well is improperly sealed or has a crack, or it's not, it's not up to code, and so somehow things from the surface are getting in there. It could be that there's a very local source if you have a really shallow well, or maybe your well's not grouted properly. I mean, there's a lot of things that could be, including your own septic or livestock. In many cases, it is, like I had a case where someone, I think it was in Virginia, they said, well, my well is out in the middle of our yard, there's nothing around it, but we test for coliform and we keep getting hits even after we shot chlorinate it. So I said, send me a picture. They sent me a picture, and they've got an 18-inch diameter tree about 2 feet from their well, and it's a PVC cased well. And I said, well, here's what's happened. The roots are going to find water, and they're going to find the less resistance. So they've wrapped around your well casing and squeezed it as they grew and probably cracked the casing. So they needed to remove the tree regardless if they're going to leave their well there. And they probably, what I suggested is they try to put a liner in and seal it so that if that was possible, and they were going to talk to a well driller to see if it was. But you can't have anything near your well if you want to, especially things like that. And even though the tree was there, they didn't get that it could be causing that problem. So you just need to, understand what the issues are, make sure your well has a proper cap, it's properly sealed. And then if you have your well log and know how deep your well is, then that will help you understand if it's a shallow source or not in the first place. Yeah, and those are all the things you need to look at. It may be really difficult to understand if it's actually your neighbor's septic in the end. Or, I'm sorry, that's the last question. It may be difficult to, yeah, well, I guess I already answered that. So I was going back to the last one. Sorry about that. So how much chlorine to put down a well? That was one of the questions this month. There was other questions about chlorination and stuff, and so we end up answering this question almost every time. But when you shot chlorinate your well, you have to follow a procedure. You mix the chlorine so it's at a certain level. You never pour straight chlorine down your well. I've had well owners tell me, well, someone told me just to pour a cup of bleach down my well every month. That's the worst thing you can do in the world. Chlorine's an oxidant. That's not enough chlorine to actually kill any bacteria that might be in there. And as an oxidant, it's going to leach metals from your pump and your pipes and your casing. And it also, if it's a bedrock well, it could leach metals from the rock. So we looked at 70 or so guides that are out there about how to shot chlorinate your well. And we decided this one from the Minnesota Department of Health was the most useful guide. And you can find it on our class resources under lesson 10, under water treatment solutions. And you should really only disinfect your well when it needs it, as determined by sampling. So if you haven't tested your well and found bacteria, don't chlorinate it. It doesn't need it. It only needs it if you have a problem. And it's just that simple. And there are wells that get contaminated regularly. Well, that's where we talk about possibly using continuous disinfection, right? So this is a really handy guide because it shows you how to mix your chlorine, tells you how to figure out how much to make it the right level, and it even has caveats about what to do with your softener or your other treatment devices. So it's really helpful in that respect, and that's the message I think I would suggest you use. You know, you have to circulate the water in the well first. I'm going to go back. You have to circulate the water in the well and make sure that you have the chlorine at the right amount, and then you run it through all the pipes in your home until you smell chlorine, and then you let it sit overnight. And that way, if you don't know where the contamination's coming from, but there could be biofilms in your home plumbing, and that will help get rid of all that. So we had a question this month, which is a great question because we see this sometimes. I've already shock chlorinated my well, but when we retested, we still had bacteria. Well, first thing is that you shock chlorinate it the right way, because we know there's a lot of bad advice out there on how to shock chlorinate a well, and so you need to follow all the right procedures and make sure that you smell chlorine in every tap, every toilet, every shower. Let it sit overnight so that it has a chance to do its job. And even if you do that, sometimes it may not work. You may have to do it more than once. And sometimes if you shock chlorinate it 2 or 3 different times, it'll take care of it. And if it doesn't, then we suggest that there's probably a continuous source. And so if that's the case, just like the spring or the well under the influence of surface water, you should probably consider UV or continuous chlorination, continuous disinfection. In some cases, the pH is too high. Chlorine doesn't work over a pH of 8. And if you have a pH that's that high, you have to use a lot more chlorine. If it's too high, it won't matter how much you use. But you have to find a way to use an alternate disinfectant. And actually, this I should have updated this. There's a paper out now that Virginia Tech researcher had done. She's now at Northeastern on the best approach to this, but it's not. We don't have a good common sense guide for how to get your pH lower. We've heard of things like putting vinegar in a well and stuff like that, but we don't have anyone who has developed anything yet. We hope to work on that, on what to do when your pH is that high. If you want to try to use chlorine, could you find a way to still chlorinate? And we hope that, we just don't have that yet. There's also a case that depending on the chemistry, you could have other things reacting with the chlorine, and that means you might need a higher dose. And if, when you start, you've mixed it in the well and it's supposedly, 300 milligrams per liter or whatever it's supposed to be, if when you get it all to your different taps and stuff, if they don't all smell like chlorine, then it's getting used up before it gets there, and you may have to do it again or use a little higher dose to take care of that. So it can be complicated. Many people shock chlorinate their wells and it works just fine the first time, as long as they've done it the right way. Parts of a well. Someone asked, that's their question, parts of a well. Well, we have a training video on that, 6 minutes long. It's under, if you go to webinars and events and say past webinars, or go on the front page to videos, it brings you to this page, and you can click on training videos and find this. I'm not going to go through it today. There's a lot of things that people ask every month that they would know if they took our class, and that's the simplest way to say it. It's already in there, and you need to do your due diligence as a well owner and take the time to go through those lessons. Many of the calls I get are when people have a problem. The idea behind our class and the work we do is to help people understand enough about their well that they can solve their problems and have an understanding of why something happens, so they can take care of it and not have to deal with it other ways. If a well gets disinfected and seems fine, but then every 3 to 4 weeks a sulfur smell starts, could that be a surface contamination creeping in problem? And there was more to this. Someone in Oklahoma, they have red clay as for the upper part of their aquifer, but it's not a surface contamination problem. It's due to natural reactions in bedrock if the well goes to bedrock. or it's from sulfate reducing or iron bacteria in your well. And again, those are common in groundwater and they can exist in groundwater, so it's likely just there. And if it gets in your well and starts growing, forms biofilms, that's where you start to get the smell, can get in your lines in your house. But if chlorination worked before, then it's likely bacteria, not sulfur in bedrock. And chlorine will work, and it also oxidizes the gas so that it eliminates the odor. So I think your choices really are, it's going to come back in all likelihood, in my opinion. So you probably want to go to continuous chlorination, or you're going to be set trying to disinfect every 3 to 4 weeks in order to take care of that. Yeah, and you can feed continuous chlorine. They make systems for that. It doesn't have to be at some high level where it really tastes like a pool. It just needs to be enough that it'll keep from bacteria growing and eventually take care of the slime that may have developed. And when it starts growing, that's when you start seeing that sulfur smell. Can you discuss contamination of a well water by iron bacteria and cost-effective and efficient ways to treat and maintain? Left any out, sorry. There's really no construction options here. As I mentioned, iron bacteria just exist, and so they're very prevalent in groundwater. So really it's to treat using chlorine, and it may need continuous treatment, as I mentioned before, and not just shock chlorination. The person that had the question before, it's really unique that the smell goes away for 3 or 4 weeks and comes back. But it's probably easier just to buy a treatment system and put it on a low dose. And I talked to a treatment professional about that, and the same for this. You'd want to add continuous chlorination. I'm interested in treatment options for arsenic. So I pulled this from the New Hampshire Department of Environmental Services, from another presentation I gave. So there's really 2 approaches to arsenic treatment in a home. There's point of use arsenic absorption media, and there's RO, reverse osmosis. I've heard a number of folks talk about putting in a full house system. That is not necessary. And if a water treatment professional tells you you need whole house treatment for arsenic, call me, because I talked to the Minnesota Department of Health. I am not a health professional, but I asked them, is there any danger of someone taking showers or anything else with water that has arsenic, even up to 150 or 250 micrograms per liter, or ppb? And the answer was no. It's really a ingestion problem at levels over 10. And so, especially for RO, I'll say that you waste a lot of water with an RO unit, and if you're doing it whole house, you're using a lot of energy and water. It's like 4 to 1 or 5 to 1. You get 1 gallon for every 5 you treat. And it's best just to, what most folks do is they put a unit either on their kitchen tap, if it's a media filter system, or if it's an RO system, they put it under their sink, and they have a separate line that they end up, like where your pull-out sprayer line goes, that they use for their drinking water and their cooking water. That's arsenic, and that's really all you need to do. I circled NSF ANSI standard 53, which is for absorption media filters, and NSF ANSI standard 58, which is for RO. Because there's a lot of treatment equipment out there that claims to be able to take out arsenic or other things, but there's 3 certification bodies that are independent third-party testers: NSF, National Sanitation Foundation, UL, Underwriters Lab, and the Water Quality Association and their Gold Seal program. If you buy treatment equipment and it doesn't say it meets ANSI or NSF ANSI standard 53, or it doesn't have one of those 3 symbols on it for UL, NSF, or Water Quality Association, then you're taking a risk, because they haven't tested it by a third-party tester to ensure that it actually meets the requirements of the standard. And so this is a voluntary program. It costs more money to put you develop a new treatment system and you want to sell it, it costs you money to one of those organizations to have them do that third-party testing. And so some folks put stuff out there that isn't. But as a consumer, I would much rather pay the extra money and know I'm getting a device that's taking things out than getting one that's not certified you're putting yourself at risk. And that's just that simple. And so, yeah, those are really your two options. Wells in this part of Maine are hundreds of feet deep. Is it more risky for arsenic or radon? Well, Maine has a great private well program, state program, and they're with funding from CDC through the Environmental Public Health Tracking Network, which is a national program many states participate in. They've got a data portal that's full of good water quality information and related private well information. So Google Maine Tracking Network. So I went ahead, I try not to do state-specific ones because this is a national audience and I'm not an expert in Maine necessarily, and so I can't answer those kind of questions, right? But I went ahead and included this. It's a reminder to all of you, do your homework. You know, if you live in Maine, you should know about the Maine Tracking Network and the data portal, where you can look at maps that show where arsenic's high, where radon's a concern, and I'm not 100% on the radon one, but a lot of other contaminants that are prevalent in Maine. And Maine is a very high arsenic state, no doubt. And Maine's also one of the states that has more private wells, people living on private wells, than people on community water supplies. And I think that just went past 50% a few years ago. So it's a big issue for Maine. But if you live in Wisconsin, for instance, I just showed you a little while ago how you can get on a website and look at the water quality by county or township for a number of constituents. And there are a lot of other states that are starting to make this kind of information available. So do your homework. And if it's not an online available source like Maine's or Wisconsin's, you're going to find the right organization, whether that's a DNR, a DEQ, whoever, that you can reach out to and maybe find the right person who will most likely be very happy to help you understand your water quality. And you should reach out to those folks and make them a resource for you, because they know a lot more about your well water and the potential water quality concerns you have in your state than I do. Okay. Is there any specific geologic conditions that require use of a topside pump, above ground pump, versus using a more common submersible pump? Or is a pump of choice by economics? You know, it's really a driller question. I'm not a driller. I'm a groundwater hydrologist. And, you know, I see mostly submersible pumps. I think they're more efficient. They typically last longer. You know, they're always cooled, right? And I think that's really if a pump gets really hot, is part of its downfall, and they don't last as long. But if your water level is really shallow, you mentioned 25 feet, that's kind of the rule of thumb for where you can use a surface pump, a suction pump. But they make jet pumps that are like suction pumps, but they also push water down, and so you can have those a lot deeper. But I would start talking to drillers, maybe more than one, or your state drillers association, and ask them this question, because I don't know the answer for sure. I just know that, you know, in many cases here, our water levels are greater than 25 feet, and I'm sure it's much more energy efficient to have a submersible than a jet pump in most cases. So it's probably a cost for them as well as what they're used to installing. It's some of all that, you know, just like, you know, I mentioned the driller who drills through sand to get to bedrock because that's all he's ever drilled. You know, he's the 70-year-old gentleman who's been drilling for 40 years and everybody knows him and trusts him. And that's the facts actually in that case. But he's not doing anybody any good services. So I'd, you know, do your homework is again the bottom line. But I'm pretty sure they're more efficient. Submersibles are, and because they're cooled by the water in the ground constantly, they're less apt to have any of those temperature changes that, you know, start to warp seals and all those things. That's my guess. There were several questions about chips versus concrete versus bentonite slurry, and those are all in relation to grout. So if you don't know what grout is, when you drill a well, you drill a hole bigger than the casing. So let's say you put in a 7 7/8 inch hole, that's the bore hole. You might put a 6-inch well casing in there. So the area between the 7 7/8 hole and the outside of the casing is the annulus. You have to fill that in with something so water can't run down the side of the well casing from the outside and get into your well and cause water quality problems. So you have to grout the well with something that's impermeable. So that can either be concrete or bentonite chips or bentonite slurry. You can trim it in. If it's a slurry, you can pump it. And so the first consideration there is what your state or local well construction code is. Some states have also county codes in addition to their state code that you have to follow. And this also gets to a licensed driller. You should use a licensed driller, not do it yourself. That's just you're taking a risk with your family's drinking water. And I could probably drill a well. I've worked on a rig and put in a lot of monitoring wells, but I don't think if I was going to live in the country, I would. Even if I had the opportunity to use a rig, I'd put in my own well. I'd let a professional do it. But the big thing I want to mention here is Nebraska in the early 2000s did a grout study. They worked with several of the grout companies, and this is the Nebraska Department of Health and Human Services, so state agency that regulates drillers and construction in Nebraska, not some independent study or anything like that. This is a state agency. So they found basically that bentonite chips were the only grout that actually stayed in place under all geologic conditions. And when I say that, what they did is they tested different kinds of grout in different geologies. And what they found, especially bentonite or even bentonite or slurry or other kinds of slurries that were pumped in, didn't necessarily stay in the annulus and stay sealed. And they did that by using clear pipe. And then they saw what happened, and they could see that it didn't stay full around the annulus. And so what's really odd to me and to a lot of folks is that when that happened, they put this out, let everybody know, and the only state to change their well construction code was Nebraska. Now, I talked to someone, I believe, from New Mexico, one of their state agency, and they were working on changing their code. When this all came out, I was so glad. All the wells I installed in the 90s, we used natural bentonite chips, and we always felt like those gave us the best chance of getting all the way down in the hole. We were using 2-inch monitoring wells, and it turns out they're the one type of grout that will stay in place. And so, like I said, most states haven't followed their recommendations. If you want to learn more about it, we had Tom Christopherson, I think it's Christopherson or maybe Christensen, from Nebraska DHHS talk at our conference about this, and you can find that video under our conference page, or you can just Google Nebraska grout study to find out more. But it was in all the drillers magazines back then and everything else. And I know the drillers magazine that NGWA, the National Groundwater Association, puts out has a article that'll come up as one of those first results about kind of a synopsis of all that they found. But it's interesting because we have all these regulations that require grout, but in some conditions it doesn't necessarily mean your well's still protected. And that's not to strike fear in everybody. I'm sure in most cases it's fine. It was tested in way back when and all that stuff, but it's just there's certain geologies where you have to be careful. And it's too bad that hasn't been more accepted. Yeah. So another really individual question here. It says, we live close to the West Fork of the Gila River. I'm probably butchering that name. It's in the Gila Wilderness. And they want to know, can flooding, this is a much longer question, by the way. They want to know if flooding can crack a casing. They also, after several flooding events, they had either orange or black water coming up in their well. And there's a hot springs nearby that has the same orange color, and their well's 82 feet deep. So, the only question I can really answer there is it's very unlikely that flooding would crack a casing. Those have to meet certain PSI, even if it's PVC recommendations or restrictions or whatever. So I really doubt it could crack your casing. But if it's a bedrock well, which you're talking about hot springs and stuff, and when I looked in that area on a map, I'm assuming that you have a bedrock well. And if that's wrong, then this won't necessarily make a lot of sense. But since most bedrock wells aren't cased the entire length, and once in a while, if it's a certain type of rock, they may cut holes in the actual pipe for water to come in rather than stop the casing and use an open hole. Because especially if it's sandstone, the open hole might not stay open. And so then in those cases, they might have to put casing down much further and basically almost screen it in a way. But I'm assuming that your bedrock well isn't cased the entire length. And that's one of the things that would be you need to know But if it's black and orange typically is manganese and iron. If it's more black, it's usually got a combination of manganese and iron. If it's more orange is red, then it's mostly iron. But you didn't mention in this if you've done any testing. And again, that's the first thing to do, is to test your water and find out what you actually have. And so I'd be glad to help and possibly talk to some folks in New Mexico, assuming that's where you live, on your behalf. But I need a lot more information, and really, if you email us, we can set up a call. And I just wanted to include that one again because it's a really unique situation, but people have those. We're working with one in Illinois now where they have, I've never seen water quality like this, and we're not sure what to do. And it's just sometimes it's just bad luck where you happen to put in your well. So we do have a few extra questions, so that's what I have for today. I'm going to quickly go to those and bring this over. And let me make that bigger real quick. There we go. Okay, so can an open old well pose a hazard to the aquifer? Obviously a safety concern. Well, it depends on if the open old well is actually getting water from the aquifer or if it's getting from the water table. I mean, it's still a hazard because it can still seep out into, if it's close to the top of the aquifer. Maybe the aquifer, I mentioned where I grew up, the aquifer was at 75 feet and our well's only 14 feet deep. An old well like that water's not going to get down to the aquifer probably. It's almost all clay in between. But it just kind of depends on the situation. But again, especially an old well like that, the best thing to do is to seal it properly. And that means using bentonite and, every state has a little different rules for how you seal an abandoned well. But I know like in Illinois, our soil and water conservation districts will help cost share that. And so it may be not that expensive to get your well sealed, and I certainly would do it. It's just a risk you don't want to take, especially, kids or grandkids. I mean, it'd be the end of the world if someone that you care about, or anyone actually, but especially someone you care about got hurt because you didn't take care of that. How often do you recommend a private well owner test for all components with E. coli, metals, nitrates versus just bacteria testing? Well, we recommend for all the metals and everything else, we recommend testing for coliform. And if you have coliform, then you want to test for E. coli. You don't need to necessarily test for E. coli the first time. You can if it's part of a package, I guess. But we recommend testing for nitrate and coliform annually because they indicate that there's a pathway into your well, and that's a problem you need to deal with, separate from whether your water quality is good or not at the time. But for everything else, metals and inorganics and stuff, we recommend every 3 to 5 years. Because one thing we've learned, unless it's a fairly shallow aquifer, and this isn't always the case, but some contaminants just don't change in value. If it's in the 30s, 10 years later we sample a monitoring well and it's still in the 30s. If it's 3, it's still 3, and that doesn't hold for everything. But I think what we've seen from other states and what we recommend, sampling for everything else should be every 3 to 5 years. What about performing strategic coliform sampling? Samples closest to the well before and after treatment to possibly pinpoint the contamination source, whether, what am I doing here? Got this too big, I guess. Whether well or inside plumbing treatment issue. I would say you'd want to do that if you have a problem and you can't, a shot chlorination doesn't solve it. I mean, it's something to consider if, you're at the point where you're going to need to add continuous chlorination or UV or whatever. But trying to pinpoint that's probably for a professional to do. I know there's a well driller in Illinois that does about 1,000 disinfections every year for people. And some of the stories he's told me, it's taken them, 6 months to over a year to finally figure out what's going on. And in some cases, maybe they had a dead end line, which is a pipe that goes to nowhere. It's just got a cap on the end. Well, water's not going to move through that. And so it's gonna, if any bacteria gets in that and settles in that part of it, it's just gonna grow, right? Or he's talked about even whenever you're shock chlorinating a well and you have chlorine at the right concentration, you run it through all your pipes. If you have a lot of bacteria or biofilms in one spot, it can eat up all the chlorine in that spot. And in a few cases, they found where if they move the water every couple of hours, they have better performance. That's not something I would recommend unless you really have an issue like that, and you've tried it 2 or 3 times yourself. But yeah, you certainly could try to do that, but I think you could drive yourself crazy, because unless you're testing how much chlorine's in the water at each of those points, you can't even be positive that the chlorine you think is getting there is actually getting there. As I said, there's things that could be in the water that could eat up some of the chlorine before it actually has a chance to get to the bacteria or the biofilms. And so, yeah, I mean, you certainly could try it, but I don't know that it's the best way to go. And even if you found that out, if you start taking your lines apart to even do the treatment, once you've discovered it's in some line in the house, that's a whole lot of mess and a whole lot of probably plumber that's going to have to be involved in all of that. And so I don't know that it will actually, certainly not a more economical solution, I don't think. So, okay, that's all we have for today. If you're looking for CEs, here's the email address. I forgot to mention probably that there are handouts, and they're the certificate of completion and the agenda. Sorry, Katie, I forgot to mention that today. And but if you have any more questions, there you go. Thanks for attending today. If you have any additional questions, you can email us. You will get an email in a couple hours that says thanks for participating. It's got my email address. You're welcome to email me as well. All right. Thank you, everybody, and have a happy holiday.